Hello friends, welcome back to the channel. In the last video we learned how Cache Stampede happens. A cache entry expires, thousands of users arrive at the same time, everyone gets a cache miss, and suddenly the database receives thousands of identical queries. That creates unnecessary load and can seriously affect system performance. But now an important question appears. If this problem is so common, how do real systems prevent it? That is exactly what we're going to learn today. And by the end of this video, you won't just know the solution. You'll understand why it works, how it's implemented, and when it's used in real backend systems. Think like a backend engineer. Imagine you're building an e-commerce application. A popular product page suddenly goes viral. 10,000 users open the same page within a few seconds. The cache has just expired. Every request reaches your backend. Now think carefully. Should all 10,000 requests go to the database? Definitely not, because every request is asking for exactly the same data. The product hasn't changed. The result will be identical. So making the database repeat the same work thousands of times makes no sense. We need something smarter. Now let's ask a simple question. Do we really need 10,000 database queries? No, we only need one. If one request fetches the latest data, stores it back in the cache, then every other request can simply read that data from the cache. Problem solved. But there is one challenge. How do we make sure only one request is allowed to fetch data from the database? What stops the other 9,999 requests from doing the exact same thing? We need a mechanism that gives one request permission and temporarily stops everyone else. That mechanism is called a lock. In simple words, a lock is like a gate. Only one request is allowed to pass through the gate. Every other request must wait until the gate opens again. Now let's understand exactly how this lock works inside a backend system. How locking works. Let's understand this step by step. Imagine the cache has expired. The first user opens the product page. The request reaches the backend. The backend checks the cache. Nothing is found. It's a cache miss. Now here's the important part. Instead of immediately going to the database, the backend first tries to acquire a lock. Since no one else is holding the lock, the backend successfully acquires it. Now this request becomes responsible for fetching fresh data. It goes to the database, reads the latest product information, stores that data back into the cache, and finally, releases the lock. At this point, the cache is fresh again. Now let's see what happens to the second request. Suppose another user arrives while the first request is still fetching data. This request also checks the cache. Again, nothing is found. But this time, when it tries to acquire the lock, it fails, because the first request is already holding it. So instead of going to the database, this request simply waits. The third request arrives, same result. The fourth request. Again the same. Every new request waits because someone else is already fetching the data. Now the first request finishes. The cache has been updated, the lock is released, the waiting requests continue. But now something interesting happens. Instead of going to the database, they read the data directly from the cache. The database is no longer needed. Think about what we achieved. 10,000 users requested the same data. Without locking, the database received 10,000 queries. With locking, the database received only one query. Every other request simply reused the same cached result. This is exactly why locking is one of the most common techniques used to prevent cache stampede. But now another interesting question appears. When the waiting requests continue, how do they know the cache has already been updated? Should they still go to the database? Or should they check the cache again? That small detail is extremely important, and it introduces another concept called double-check locking. Now that we understand the idea, let's see how developers actually implement it. Don't worry about any programming language. This is simple pseudocode. The logic remains the same whether you're using Java, Go, Python, Node.js, or C++. The first step is simple. We check the cache. If the data exists, return it immediately. No lock, no database. Nothing else is needed. But if the data is missing, we try to acquire the lock. Now, two things can happen. If we successfully acquire the lock, we become responsible for rebuilding the cache. But before going to the database, we perform one more cache check. This step is called double check locking. Now you may ask, why do we check the cache again? Isn't one cache check enough? Good question. To understand the answer, let's temporarily remove the second cache check. Suppose our algorithm looks like this. We check the cache. If the data exists, we return it. Otherwise, we acquire the lock, go directly to the database, store the data in the cache, release the lock, and return the response. At first, this algorithm looks perfectly fine, but let's execute it step by step. Suppose request 1 arrives, it checks the cache. Cache miss, no data is found, so it continues. It successfully acquires the lock. Now request 1 becomes responsible for rebuilding the cache. It goes to the database and starts fetching the latest data. At this moment, request 1 is still busy talking to the database. It hasn't finished yet. Now suppose request 2 arrives. It also starts from the beginning. First, it checks the cache. Again, cache miss. Because request 1 hasn't updated the cache yet, so request 2 continues. It tries to acquire the lock, but the lock is already owned by request 1, so request 2 cannot continue. It waits here. Not at the database, not after the database. It waits exactly before the lock. Now request 3 arrives, same story. Cache miss, tries to acquire the lock, waits, request 4 arrives. Again, waits. Very soon. Hundreds of requests are waiting at exactly the same place, right before the lock. Notice something important. Every waiting request has already completed the cache check. They are only waiting for the lock to become available. Now request 1 finishes. It receives the latest data from the database, stores it inside the cache, releases the lock, and returns the response. Everything looks perfect, right? Not yet. Now request 2 wakes up. Because the lock has become available, it immediately acquires the lock. And now think carefully. According to our current algorithm, what is the next step? It goes directly to the database. Again. But wait. The cache was already updated by request 1. The latest data is already sitting inside the cache. So this database query is completely unnecessary. The same expensive work is repeated again, simply because request 2 never checked the cache after acquiring the lock. That is the real problem. So how do we fix it? Very simple. Immediately after acquiring the lock, we check the cache one more time. This second cache lookup is called double check locking. Now request 2 acquires the lock. Instead of going directly to the database, it checks the cache again. This time, the cache already contains the fresh data written by request 1, so request 2 immediately returns the cache data. No database query, no repeated work, no unnecessary load. If the cache is still empty, only then does it continue to the database. Fetch the latest data, update the cache, release the lock, and finally return the response. That tiny second cache check prevents unnecessary database queries. And that's why almost every lock-based Cache Stampede solution uses double-check locking. Quick recap. Now let's quickly review the complete algorithm. First, we check the cache. If the data is already available, we immediately return it. No lock, no database. If the cache is empty, we acquire the lock. Then, we perform one more cache check. If another request has already rebuilt the cache, we simply return the cache data. Otherwise, we fetch the latest data from the database, update the cache, release the lock, and finally, return the response. That is the complete locking algorithm used to prevent Cache Stampede. Now think about what we achieved. Thousands of users requested the same data, but only one request rebuilt the cache. Every other request simply waited. The database performed the expensive work only once. And after the cache was updated, everyone received the same cached result. This dramatically reduces database load, prevents repeated work, and protects the system from cache stampede. But locking is not perfect. Waiting requests increase response time. If rebuilding the cache takes longer than expected, every waiting request also waits longer. So locking solves one problem, but introduces another trade-off. That is exactly how system design works. Every solution has advantages, and every solution has costs. Now another interesting question appears. Instead of making hundreds of requests wait, can we merge those identical requests together so that nobody waits unnecessarily? The answer is yes. And that technique is called request coalescing. We'll understand it from scratch in the next video. If this video helped you understand locking, please hit the like button, subscribe to the channel, and share this video with someone learning backend development or system design. Your one like, one comment, one share, and one subscribe motivates me to create more deep technical content like this. Thank you so much for watching. I'll see you in the next video, where we make another hard tech topic. Easy actually.